It took 10 years, the Voyager, to travel from Jupiter to Neptune, and we have seen the link budget for Jupiter. Now we are going to see the changes that were needed to receive the images from Neptune. If we keep all the parameters we had before, then the main difference is the distance. Here on the first line we have the bit error rate that was required from Neptune, which is proportional to the square of the distance from Neptune. And if we compare this value with the value for Jupiter, we'll see that the ratio of the distances is square. So if we keep all the parameters, we need to increase the signal-to-noise ratio by a factor of 10 log the ratio of the square of the distances, and this means that we need 17 dB more of signal-to-noise ratio. So things had to change on the station, on the ground station, because we couldn't change much on the satellite except for the data rate. So the first thing they did was to improve as much as they could, and they needed for other missions, the ground stations. And with this, they got some improvement. They went from 64 to 70 meters, which is not an easy task, just to increase the diameter of the antenna. The gain, that was 63.2 dB at 2.1 gigahertz, was increased, that was before different value was increased to 63.2. That meant 1.9 dB of gain at this band. And also, they managed to decrease a little bit the noise temperature under clear sky. So they got 18 degrees at the zenith when looking to the atmosphere, and 21 at 30 degrees elevation. That increase in noise temperature is mainly due to the fact that when you look to the zenith, you just go through the minimum length of atmosphere possible. But if you just go near the horizon, then your path is much longer across the atmosphere. So you have losses, absorption, and added noise. That's why you have a higher temperature, noise temperature there. At X-band, the antenna gain went to 73.5 dB. That was an 1.8 dB improvement. And again, the system noise temperature was improved somewhat. So this is just the balance of the improvements. We got about 1.8 dB of gain by going from 64 to 70 antenna diameter. By lowering the noise temperature, we got about half a dB. It's not that much, but that's make a total about 2.3, 2.4 dBs of gain. So the only way we still could improve was by decreasing the data rate. And this was what was done. At Jupiter, the images were sent at 115 kilobits per second, and from Neptune, this data rate was decreased to 21.6 kilobits. In total, they managed to get 9.6 dBs, but the problem is that that was not good enough to receive the images, so they had to begin putting more antennas into reception. And what they did was to array the 70 meters antenna and the two 34 meters antenna that is at each side, and also to combine them with the 27 antennas at the VLA places that you are going to see now. So those are a long number of antennas, each one of them with a 25 meters of diameter, and combining those things, they managed to get a margin of 5 dBs, and with this they could receive the images from Neptune. And just to finish with some images, that's the way things look. This is the ground station. This is one of the three antennas in Madrid, Canberra, and Goldstone. This is the very large array, the VLA, in Socorro, New Mexico. Here the antennas could move on a rail track, is a Y shape, and they could place the antennas at different spaces. At the beginning, those antennas were all connected with physical cables, with microwave cables, just to join all the signals they could collect and add them. Now they are individually managed, and they all have atomic clocks just to synchronize the signals they receive from space. And some images that probably you all have seen very frequently. This one is from Jupiter. This is the great red spot, has been known for almost 400 years. It's a very stable storm, and the size of the storm is larger than the Earth diameter. In fact, Jupiter is about 10 times also the Earth diameter. So this is really a very stable and large. This is Neptune. It's an icy planet. The gas contained here is different. Hydrogen is in much lower quantity than is in Jupiter, and the blue color in Neptune is due to methane. And this is a nice image that was really sent. There were many, many more images that you can find in the NASA website, especially of the moons of those large satellites. Of those large planets. And there are many satellites involved in this case. Now, when Voyager 1 was leaving the Earth, Carl Sagan, you probably heard about him because he was the man behind the Cosmos series and behind this project, asked NASA to turn the cameras and point towards the Earth. And on Valentine's Day of 1990, 25 years ago, then they really got an image from the Earth, and that's how the Earth looks from space. And it's just one single dot. And Sagan named this picture a pale blue dot, and he used this picture in his books. So this is the Earth seen from space, almost just the point, the pixel in an image. Now, to finish, let's comment briefly on this. Today, still those spacecrafts are sending data to Earth. They are not sending images, certainly, but there was one remaining planet at the time that was not really explored, and it's Pluto. So NASA sent 9 years ago a new probe to explore Pluto, its moon Charon, and afterwards the Kuiper Belt. Pluto is the largest body in the Kuiper Belt, and this is how the spacecraft looks like. And you see it's very similar to Voyager. The antenna is 2.1 meters, so it's a shorter antenna. It has more or less the same structure. This is the nuclear reactor for powering the unit, and everything else are the images and the camera around there. And in this case, although the probe is very similar, the main difference you can imagine is in the storage, imaging system, computing, power, coding. Everything has changed except for one thing. The distance is so great and the antennas are limited, as is the power, that still, although the encounter is going to last a few hours, on July 14 of this next summer, 2015, it will take almost a year to send the images, and the images are going to be sent down to Earth at a bit rate that will be from 600 to 1200 bits per second. So it's going to take almost a year to send the images from Pluto and its moon. And afterwards, they plan just to pass by another body on the Kuiper Belt and send images. So in the next few months and next couple of years, you're going to hear a lot about the New Horizons probe, which is the successor of the Voyager 4 years later. If you are interested, you may have some data, some additional data and images on the NASA and Johns Hopkins University websites. And just to finish, let me credit the authors and also the facilities at the Universidad Politécnica de Valencia, where this video has been recorded.